What is magnetic flux in electrical engineering? Imagine holding a magnet near a coil of wire and watching how the electric current changes. That's all about magnetic flux, a key idea in electrical engineering. Magnetic flux measures how much magnetic field passes through a surface area. Think of it as counting the magnetic field lines crossing a surface. The more lines that go through, the higher the magnetic flux. It is represented by the Greek letter phi, or sometimes as phi or phi b. To find the magnetic flux, you multiply the magnetic field strength, which is measured in teslas, by the area of the surface in square meters, and then by the cosine of the angle between the magnetic field and the surface normal. The formula looks like this. Magnetic flux equals magnetic field times area times cosine of the angle. If the magnetic field is directly perpendicular to the surface, the cosine of the angle is 1, so the flux is just the magnetic field times the area. If it's at an angle, the flux decreases because fewer magnetic field lines pass straight through. The unit used for magnetic flux in the International System of Units is the Weber. 1 Weber equals 1 volt-second. In simple terms, magnetic flux tells us how much magnetic field flows through a surface. This concept is essential because when magnetic flux changes around a coil or conductor, it causes an electric current to flow. This is described by Faraday's law of induction. According to this law, the electromotive force, or EMF, generated in a circuit is proportional to how quickly the magnetic flux changes. The faster the flux changes, the stronger the induced current. The formula for this is EMF equals negative number of turns times the change in flux divided by the change in time. The negative sign indicates that the induced EMF opposes the change in flux, following Lenz's law. This principle is behind many electrical devices like transformers, generators, and motors. For example, in a transformer, when the magnetic flux in the primary coil varies, it induces a voltage in the secondary coil. In electric generators, mechanical motion changes the magnetic flux through coils, producing electrical energy. To measure magnetic flux, devices called Fluxmeters are used, which detect voltage changes caused by flux variations. Understanding magnetic flux also involves the magnetic flux density, which describes the strength and direction of the magnetic field, and magnetic reluctance, which is how much a material opposes the flow of magnetic flux. In essence, magnetic flux is a fundamental idea that helps explain how magnetic fields interact with electrical circuits, making it possible to design and operate many electrical devices we rely on every day.